Shall we start the session, Biplav?
Good afternoon, Padmanabhan sir.
Yeah, shall we start now?
Yes, sir, we can start. Good afternoon, to all participants. Sir, there are only 82 participants till now, so we can wait for 1 or 2 minutes more.
Sure, sure. Let me know. We'll
Okay.
start. Yeah.
Good afternoon, everyone. Welcome back to second session of day 2 of this online joint faculty development program on designing with FPGAs. So the second session includes timing exceptions and timing analysis and timing closure. These will be 2 sessions will be taken by Padmanabhan sir. Padmanabhan sir, I made you the presenter.
Thank you so much, Biplav. I'll start the presentation.
Okay, sir. Over to you, sir.
So good afternoon, everyone. Welcome to the timing exception session. Here we are going to discuss on the multi-cycle paths, false paths, and how are we going to ensure that the design is having a multi-cycle path and what kind of exceptions that need to be set. We are going to see a lab demo. And followed by how are we going to constrain the input-output paths, like input to register as well as register to output paths. And we can also see how do we achieve the timing closure. How do we ensure that the design is not having any setup or hold violations? We will discuss that in detail. And then let us explore the next information. So when we see what are timing exceptions, let us take the example of a multi-cycle path. Paths where the default selected launch or latch edge causes an incorrect timing analysis. So in general, how do we define a multi-cycle path? If you say a multi-cycle path is a path which takes more than one clock period to propagate the data from one flip-flop to another flip-flop. So that means if we wanted to propagate the data from one flip-flop to another flip-flop, usually it should take only one clock period. That's what we discussed in the morning, which is an ideal case. But there are situations where you may require more than one clock period to transfer the data from one flip-flop to another flip-flop. We call that as a multi-cycle path. So it causes the timing analyzer to select another latch or launch edge. Because of that, the designer needs to specify number of clock cycles to move the edge. That's what we call this as a multi-cycle path. Logic must be designed to work this way. If doesn't, it simply loosens the timing requirements. So now what we are supposed to do is, if we wanted to make the design to meet timing, then it is very critical and important that we should specify multi-cycle paths in the design. Okay, how do we find out is there a multi-cycle path in the design? I will show you a demo based on the multi-cycle path, which the same lab we can do in the hands-on section. So when we say a multi-cycle path, when we specify a multi-cycle path, how do you specify that? When you say we need to specify from, and then you need to specify to. We can see that in the from, you can see there is a clock, and to you can see which is clock 1. That means from clock to clock 1, you are transferring the data. And it is not going to take only one clock period, because the launch flip-flop is 1 clock and the capture flip-flop is another clock. So how are we going to solve this problem is by a multi-cycle path definition. We should specify here value 2. That means it takes 2 clock periods to transfer the data from one flip-flop to another flip-flop. So from to defines the path, and value is the number of clock cycles, n is the period, and analysis type is either setup or hold, depending on whichever check you wanted to provide. And the reference clock is the one which describes how we can perform setup and hold time. Okay, so this is what is specified in the multi-cycle path. So let us understand the concept of multi-cycle path, and then we will understand which design require multi-cycle path, and then we will go ahead with the lab demo. Which of the two designs requires a multi-cycle path? There are two designs available here. If you see design 1, that shows that the launch flip-flop is 50 megahertz and the capture flip-flop is 100 megahertz. Now from 50 megahertz to 100 megahertz, we have to transfer the data. This is design 1. Design 1, the launch flip-flop is having a 50 megahertz clock and the capturing flip-flop is having a 100 megahertz. Whereas in the design 2, the launch flip-flop is 100 megahertz and the capturing flip-flop is 50 megahertz. Now, which design requires a multi-cycle path? When you say design 1 requires a multi-cycle path. Why? Let us explore that in detail now. If you see 50 megahertz clock, you can see that this is 50 megahertz. And this is the 100 megahertz clock, right? So this is 100 megahertz. Now you can see that it requires 2 clock periods to transfer the data from one flip-flop to another flip-flop. So this 50 megahertz, if you see 100 megahertz, it requires 2 clock periods, not 1 clock period. If you try to constrain it 1 clock period, that means it's only half cycle. Therefore, we will be in trouble. So this requires a setup, which is a multi-cycle path of 2 clock cycles and a hold multi-cycle path of 1 clock cycle, because the whole analysis is done on the launch edge. Therefore, it has to be done with only 1 clock cycle. Whereas the setup analysis requires 2 clock periods. That's what we need to do here. So this is what we call the setup multi-cycle path constraint. So what we have done in the morning is we applied the clock constraint, and then we have applied the set max delay and set min delay for a pure combinational logic block. Now what we are going to apply is a multi-cycle path constraint. That means that particular path requires more than 1 clock period to transfer the data from one flip-flop to another flip-flop. Okay, how do we solve this problem? Let us understand that right now. Okay. Let me directly take you to an example where how are we going to solve the multi-cycle path. Let us see that. Okay. That is our lab for the day, which is called as a multi-cycle path extension lab. Let me open the timing lab manual, and we will directly go to the multi-cycle path example. This is what would be shared with you. So let us try this multi-cycle path example now. Okay. Right. Before getting into the details of the multi-cycle path, this is the timing analyzer.qar file, and this is the multi-cycle path.qar file. Let us take the multi-cycle path.quartus archive file. We go to the C drive, create a new folder, and say timing exceptions, and say IIT G and say FTP, something like that you take. Inside this folder, what we are supposed to do is like we paste the multi-cycle path.qar file. Right, let us open the Quartus Prime Design software. We close this project. Click open project. To understand the steps, then you can also practice during our hands-on session. Go to the C drive and say timing exceptions lab. Inside that you have a multi-cycle path.qar, which is the Quartus archive file. Just say open. Right, now if you open the Verilog code, you can see that. Okay, so let us save this. If you go through the Verilog code, you can see that always at passage of clock, you have a 333 megahertz. And always at passage of clock, you can see that is 666 megahertz. So here you have 333, and then here you have 666. That means you have two clocks, right? Now, you can also see that at 333 megahertz clock, what is there in A, that is taken to reg A. What is there in B, that is taken to reg B. At 666 megahertz, we copy that what is reg sum, that is taken to sum. Okay, let us analyze the design first. Let us perform analysis and elaboration. Okay, when we perform analysis and elaboration, just open the schematic. If you see the RTL viewer, you can see there are two clocks. One is the 333 megahertz clock. Another one is the 666 megahertz clock. Now, we can also see that you need to cross this logic level, and then it has to reach the data pin of the flip-flop. Whereas this 666 megahertz clock is directly connected to this flip-flop. There are chances that you have to cross this flip-flop, you have to cross this adder, and then you should reach the D. There are chances that before it reaches the 666 megahertz clock can reach this flip-flop. This is dangerous. Okay, let us perform synthesis and see the synthesized schematic. So let us perform full compilation. Okay, after we perform, you can see that what happens in the schematic. Let us go to the netlist viewers and open the technology map viewer post mapping. So you can see that how this is getting connected. Okay. Similarly, let us see the schematic of the post fitting. Right. So you can see that what is the kind of multi-cycle path primitives and ports it takes now. Right. Let us go into the timing analyzer. Tools and move into the timing analyzer. Okay, and open create timing netlist. And let us see report clocks. How many number of clocks are there? You require 3 clocks. One clock is 333 megahertz. Another clock is 666 megahertz. So period is 3 nanoseconds. One is 1.5. So both informations are provided. Now, what do we need to do here is like when we try to see report timing, what is the problem? That's what we need to understand. So let us first explore by clicking the report timing tab, go to the setup analysis and say report time. You can see that the paths are violated. Why the paths are getting violated? If you see, there are 2-3 things we have to understand here. The first thing what we need to note down is, you see the waveform here, where it shows this is the launch edge, and then it shows this is the latch edge. But this should not be the latch edge, because when you launch here, you should capture here, because this only completes the full clock period. Whereas what we are trying to do is we latch here. This is only half cycle. Because since it is a multi-cycle path, since it is a slow logic path, it requires more than one clock period to propagate the data from one flip-flop to another flip-flop. Instead of here, it should be here. But what we have done is, by mistake, we were expecting that it should work in this, which is definitely not possible. Right. Now, another important information is when you click path summary, it shows that what is the required time, that is 4.8, but what is the arrival time? If you see, it shows 5.461. That means the RT minus AT becomes a negative number. That's what is the problem for us. How do we still explore this? When we say we can click the path and go to the locate path and then see that path in the technology map viewer. When we see that path in the technology map viewer, you can see there are more number of logic levels between that flip-flop. Between this launch flip-flop to capture flip-flop, you can see there are so many number of logic. It has to cross so many logic levels and then it should reach this flip-flop. And you say there are chances that before that the clock can reach. And we knew that this is a slow logic path because it has to cross so many number of logic levels. So now there are only 2 options for us. One, while writing the code itself, we should ensure that there should be minimum number of logic levels between the flip-flops. Or else, during the timing analysis, we should tell the tool it is an exceptional path, because it won't take only one clock cycle. It will take more than one clock cycle because it is working on a slow logic path, because it is a kind of multiplier output or anything where you will be getting output every 4 clock cycles. You won't be getting the output of the multiplier every cycle. You will be getting the output of the multiplier every 4 clock cycles. Then we have to wait for 4 clock cycles to get the data. So therefore, it is essential and important to tell the tool whether that is a slow logic path. That has been explained here. Now, what is important is we have not specified that as a multi-cycle path, and therefore it is trying to take that constraint and then applies and shows that all the paths are getting violated. Let us see the timing of one path. So report timing, and then that you can see that in terms of hold also we will check down. The hold paths are meeting timing, but then there is a problem only in the setup path, because the hold analysis is done on the launch edge. So therefore there is no worry. But all the problems are happening with respect to setup key. Right? So you can see from any register to any output, it is showing that it requires more than one clock period because of the specific summary. How are we going to solve this problem? Yes, we are going to apply some exceptions. Okay, before that, let us see, are there any exceptions applied in the design? So in the custom reports tab, you can see report exceptions. So you double click and see, are there any exceptions in the design? You can see that no exceptions were found. Please note that an exception should be of set false path, set multi-cycle path, set min delay, or set max delay. So set min delay or set max delay is for the pure combinational logic paths, which I explained you in the morning session. Set false path and set multi-cycle path we are going to apply now. So set multi-cycle path means what? We are telling the tool it will take more than one clock period to propagate the data from one flip-flop to another. But if you go through the FTC file, is there any specific path that is applied when you say we don't have, because we have only 2 clocks, no other exception is applied. Now what we can do is we can set that as a multi-cycle path. That means instead of 1.5 nanoseconds, we want that to do at 3 nanoseconds. That means you should wait for 2 clock period. So that is the way how you can solve the problem. That's the lab we are going to do. I'm going to show the demo and share the lab files with you. And you can also practice and ensure that the multi-cycle path is constraint can be applied properly. What we need to do? Go to constraints and select here set multi-cycle path. Right? In the from to setup value, these are the things we should enter. Right? What are the things we should do? First, I will tell you. On the from, you can see there are 3 dots. Click that and say list. Okay, when you list it, you will be getting 2 clocks. Take the first clock. From 333 megahertz clock, bring that on the right hand side by clicking the greater than symbol. Select it. From get clocks 333 megahertz. Again list it and take 666 megahertz clock. You say value 2 clock. So set multi-cycle path hyphen from get ports 333 megahertz hyphen 2 get clock 666 megahertz hyphen set end means 2 clock periods. After applying this constraint, say run. You can see down set underscore multi-cycle underscore path hyphen from get clocks 333 megahertz hyphen 2 get clocks 666 megahertz hyphen setup hyphen end 2. Now what we also need to do is we should apply the multi-cycle path for the hold analysis. So again we should go to constraints and go to set multi-cycle path hyphen from same you click here list 333 megahertz, bring that on the right hand side, save OK. Then again on the tab, just click list and say 666 megahertz, bring that on the right hand side. Instead of setup, you select hold and say value 1. Because the hold analysis is done on the launch edge, which is n-1. Now you can see set multi-cycle path hyphen from. For setup, it is 2 clock periods. And for hold, it is only 1 clock. Now what we can do is we can perform 2 important things. One, we are going to see report timing. Second, we are going to click report exceptions and check whether the exceptions are taken into account, right? And the tool is providing the value or not. Let us try that now. Report timing, setup and say report. Now, instead of 1.5 nanoseconds, it has taken 3 nanoseconds. You can see the relationship here. 333 megahertz to 666 megahertz. You can see that. And now you can see this is the launch and this is the launch capture. So now this is very, very important for us. Earlier, we tried to latch here because it is only one half cycle of it. It is only 1.5 nanoseconds. But then now you are latching it here. How do we know that it is a multi-cycle path? When you say, we can click the path summary. In the path summary, you can see it shows launch clock is 333 megahertz. Latch clock is 666 megahertz. And it shows that this is a multi-cycle path and then it takes 2 clock periods. And also you can see the data required time is 6.329 and data arrival time is 5.461 and the slack is 0.868 and therefore it is meeting timing. So now what is very important for us is we can say that it is a multi-cycle path. But then now you can click and go through the path, but then there is no difference. But what is important in the earlier case, we wanted to get that in one clock period, which was definitely not possible because of the slow logic path. But now it is possible since we gave 2 clock periods. This is very, very important for us. And this helps us to understand how do we constrain a multi-cycle path. So this is for the setup analysis. Same could be done for the hold analysis. You double click and you select hold here and say report time. And go to the path summary. You can see multi-cycle path setup 2 and multi-cycle path hold. It shows 1 nanosecond. Arrival time minus required time is the positive. All right. Please understand the hold analysis is done only on the launch edge. So launch is also same edge. Latch is also same edge. Right. Now, the earlier case when we clicked report exceptions, it was not showing anything. But now can we try that? When you say yes, we can try that. Now we can say report exceptions, double click, and we can say setup. You can see that. Set multi-cycle path hyphen from 333 megahertz hyphen to 666 megahertz value 2. This is for setup. Same report exceptions, we can double click and select hold and say report exceptions. Now you can see it shows 1. This is the way how you can apply timing constraints to a design, the multi-cycle path constraints to a design, and check whether it is meeting timing or not. That's the base idea. So this is very, very important for us because without applying the specific timing exceptions, we cannot complete the time. Now it shows that the status, you can see it is complete. The exception is applied and the timing analysis is complete. Okay, so this is the one which you need to do. So in the lab manual, if you go through, this is the multi-cycle path example which we need to go through here, where you can see, you can compile the design, you can open timing analyzer, and as I showed, you have 2 clocks, 333 and 666, and you can say constraints and set multi-cycle path, and for the setup analysis, you should give 2 clock cycles, and for hold, we should give 1. After you provide that, you can write constraints to the SDC file. That's what I'm going to show you right now. At the end, what you are supposed to do is you can go to constraints and say write SDC file, and you can save that into the SDC file. Right now, what you can do from the C drive, you can check whether the timing constraints are written. Inside that, you can see multi-cycle path out.stc file. Here you can see create clock. Both clocks are available. Now you can see set multi-cycle. The first one is for the setup. Second one is for the hold. For setup, you can see it is 2 clock periods, and for hold, it shows 1 clock period. This is the way how you can try that. Right, this is the basic logic of a multi-cycle path constraint. And let us explore another important timing exception called as false path. I will explain that also. In the next timing exception, what we need to discuss is called as a false path. So what is a false path? Let us understand. Paths in a design that physically exist but will be never exercised by the circuit. That is called as a false path. They are available, but they will never be exercised under any input conditions. So how you can define is a false path is a path which cannot be sensitized under any input conditions. Any input conditions you pass, it won't, that paths will never get sensitized. They are available in the circuit, but then they will never get sensitized. Then those paths are called as false paths. Okay, why we need to be very careful about the false paths when you say the STA tool, what we are doing, right, does not require any test vectors, I told you. It is going to check only timing. So now what we wanted to do is, as a designer, we only know that what input we are going to pass, either 0 or 1, right? So we have to be very careful. because the tool will show that what are the timing paths that are available based on the input and output. It won't show you the paths in terms of the test vectors what you are passing. So we have to be very careful. So specifying a false path removes it from timing analysis. When we specify a false path, what is the advantages? We can ignore that path from performing timing analysis. That would be a very good idea for us. So by specifying a false path, the greatest advantage what we can get is we can tell the tool that you ignore that path in performing timing analysis. That is very, very important for us. Right. So let us take an example. If you go through this circuit, where you can see what are the different type of timing paths you have for this, we can first find out. But please ensure that select line is common to both multiplexers. If you ask the timing analyzer tool to list out how many number of timing paths are there in this design, it will show you 4 paths. One is A, T, T1, T2 out. The other one is A, C out. Then B, B1, B2, C out. Then B, B1, B2, C, C1, C2 out. So the timing analyzer tool will show you 4 combinations of the paths. But as a designer, we only will know that whether all the 4 paths are valid or not. Let us assume if the select line is having the value 0, then which paths will be activated? Let us see. If the select line is having 0, that means both multiplexers will have the select line of 0. What will happen? B, B1, B2, C out will be there. Now when the select line becomes 1, then you can see that it takes like A, C, C1, C2 is there. Out is there. But what may not happen is B, B1, B2, C, C1, C2 will not happen. A, C out will not happen. But the timing analyzer tool will show us all the 4 paths because you have an input, you have an output. It starts from an input port, flows through the combo logic and ends at the output port because they are the valid start points and end points. Now it is the designer's responsibility or the user's responsibility to tell the tool that it is a false path. If you are not specifying a false path, then there are chances that you will be ending up in trouble. Why? Let us take a simple example here. If B, B1, B2, C, C1, C2 is the longest path, let us take, and that path is taking the longest delay, then you think that that is the critical path, and then you will try to constrain your path based on that, which is dangerous. Because whether that path is valid, if you see that path is not at all valid, because it won't get sensitized under any input conditions. Therefore, we have to be very, very careful with the false paths. Okay, that is one. Now, another case is like there may be an asynchronous input, like you will have an asynchronous reset or asynchronous set in a flip-flop in a design. So it is also possible that irrespective of the clock, that path can also be taken into account. So therefore, we should tell the tool that that path is not going to happen synchronously with respect to clock, and therefore that need to be considered separate. You can tell the tool you ignore that path while calculating timing analysis because that particular path is not synchronous to the clock. That is also very important for the timing engineer to take into account. Okay, so let us see one example of that. And I will show you what is the specific principle. I will close this project. You wanted to write it, you can write it into an FTC file. Let us create a new project with that. And say false path. Okay. Let us take a simple design. You take a counter design. Let us close that. Okay, so let us try opening it once again. So what we can do is we can create a simple code, Verilog HDL code, and say module and say counter. We will create a asynchronous path here. Input, clock, reset, and say output. Right, 3 down to 0 and say Q. Now you can say always at passage of clock, comma, edge of reset, say begin, if reset, say Q is equal to 0, we'll say Q is equal to Q plus 1. And say end. Okay, let us save this file. And let us perform compilation. Let us look into the synthesized schematic. Now you can see you have an input to edge path. Also, you can see there is a reset path that is connected right here, but they are asynchronous to the clock path. We cannot say because the code when you write, we have written always at path edge of clock, command edge of reset is asynchronous to the clock. Now, when we perform the timing analysis here, we are informing the tool that you go to the timing analyzer and we create a timing netlist and we can generate a clock. So name of the clock. Then we can say in the can say list, bring the clock here and 10 nanoseconds. Let us say that. The clock is created. Here we can say in the diagnostic report clocks. And you can see it shows 10 nanoseconds. And then here we can say report timing and say report time. Now, if you see that all the paths, right, it is not trying to take anything from the input. So now you can see it also shows from only from register to register. Right, so we have to be very careful that the pin, what we are trying to use, the reset, is the asynchronous to the clock path. There are two ways to sort out this issue. Either you can do here and directly you can select here set false path and say hyphen from. You can say, then you can easily provide whichever starts from the reset pin can be a false path. If you know where it ends, then we can say 2. Whichever starts from the reset pin, right, everything is a false path when you say, then we can directly say that it is a false path. So set false path hyphen from, you can say here get underscore ports and then we can say reset. Whichever starts from the reset pin can be a false path, you can say that. So now once we provide this as a false path, then we can ask the tool, right? So can we check whether the exception is taken into account? So you can see report false path and you can say report false path. So here you can see that this is not taken into account, but then here you could see there is an exception. The path will not be analyzed because we gave that as an exception. False path hyphen from get ports reset. Anything starts from the reset, we don't want to do setup slack. It is invalid. Similarly, report exceptions. You select hold here and say report exceptions. Now we can see that for hold slack it is in. Because we knew that it is an asynchronous path and we don't want the tool to analyze the path for that. So that information can also be taken. All these informations could be provided and we can also see the custom required reports here where you can see the slack histogram. So which clock you can select. Okay, I have only one clock in the design and for that clock you can see the clock histogram. What is the slack value? That information we can see. Here in terms of slack and what is the slack value, that information you could see. Okay, if you want to save this, you can save that information now. Right. What are the other two informations which we should know? In the earlier case, I explained you about the clock latency. So all these delays, whatever we have seen so far, are the data delay. What we are going to discuss right now is called as the clock latency. That means there is a clock delays on the clock side. Now we can see there are two types of clock latency. One is called as the network latency. That means the delay between the clock definition and the register clock pin. That means the first one is called as the source latency. Delay between the clock definition and its source, where it starts. So the delay from the clock definition point to its flip-flop, there may be a delay, right? So that is called as the network latency. So the source latency and network latency, both are put together. We call that as a latency. Okay, so source latency plus network latency will be providing you the clock latency. That is one. Second one, what I discussed in the morning, is called uncertainty. The first one is called as skew difference in arrival of the clock between two different registers, I told you, and the jitter, deviations in the exact defined period. That is, frequency variation in the clock source is known as jitter. So even though both are terms in terms of uncertainty, but we are subtracting that in the setup calculations. Without uncertainty, we are verifying that whether the design meets timing or not. Okay, so what is very important in this case is, in one place, we take the clock value maximum. In another place, we take the clock value minimum. Even though it goes through the same set of components, for one analysis, we take the maximum value. For another analysis, we take the minimum value. So that information is called as clock pessimism. In the clock path, what we are trying to do for performing the setup and hold analysis, in one place, we take the minimum clock delay. In another place, we take the maximum clock delay. That means they are having the same buffers, must have the same delay component, but then we take minimum value for one and we take maximum value for other. That is called as the clock pessimism. Right. Now, what is very important and what is the thing which we need to go through is, till now what we were trying to do is to constrain register to register paths, and we applied multi-cycle path exception, false path exception, and then we have also seen how to constrain a pure combinational logic path using set max delay and set min delay. Now what we are going to understand is how to constrain an input to register path and register to output path. That is very, very important for us. So let us consider the options right now. It is called as an IO constraint. If you take the data sheet of a memory, for example, here you can see it shows clock to Q. That is the clock access time, which is 3.5 nanoseconds that is provided. Now, let us go through the FPGA here. Till now, whatever we have constrained so far is between the FPGA, register to register. Now, there is a device before the FPGA which launches the data to the FPGA. And there is another device which is memory which gets the data from the FPGA. So, your input to reg and your reg to output paths are incomplete static timing analysis paths. They will be constrained only by providing separate commands. What are the two commands we should provide is, one is called as the set input delay, other one is called as the set output delay. Why these things are important? Because we need to know who is going to transfer data to the FPGA and who is going to get the data from the FPGA. So these two information should be known to us. What information is known to us and what information need to be taken from the data sheet when you say, we know the information which is present inside the FPGA. What information is not known to us and which we should take it from the PCB designer or from the data sheet is T clock to Q of the external device. This we don't know. And the trace delay till it reaches the FPGA. This is called as the maximum trace delay. This information we don't have. So these two information we should take from the data sheet. That's what I showed you, the memory data sheet where the T clock to Q was specified. Now, after getting these details, only we can constrain input to reg path. Okay, so what is set input delay? Set input delay is the combination of T clock to Q of the external device plus the trace delay till it reaches the FPGA. This information, if we have, we can constrain the input to reg path appropriately. Similarly, on the other side, if you see, what information you know is from the register to the output port you know. But from the output port to the external device, do you have information if you say, no, we don't have. That information should also be specified. Okay, now How do you constrain an input to reg path? Here, if you see, you can see that this is the T clock to Q of the external device plus the trace delay. That information we should know. So set input delay maximum is equal to the maximum board delay, max clock to out of the external chip. This is what is T clock to Q, which is max clock to out. That's the maximum board delay. This maximum board. Minus minimum clock skew, because there may be a skew for the device that you can. And what is the minimum value? Because we require both values, both max and minimum. We have to specify. And we can specify that could be given as minimum clock to out of the external chip plus minimum board delay. So these information, we should take it from the data sheet. So without getting that information, we cannot constrain input to register path as well as register to output path. So this is very, very important for us. In same case need to be approached for set output delay. In set output delay, what is required is we need to know that who would be getting the data from the FPGA. We should know the minimum board delay and we should require the maximum clock skew. So these informations you should know. Similarly, we should require the maximum board delay. So we should know the requirement that is set up, and before the hold, the data should be ready. That's what we require, minimum hold time. All these informations need to be specified by the designer. Okay, where those informations will be when you say those informations would be available in the data sheet, and it is our responsibility to apply that and ensure that the design is meeting the timing. So without applying these constraints, we cannot say that the design is meeting. It would be a very much challenge for us, right? So that is important, and we should ensure that the design is meeting timing after applying all these constraints. So what are the constraints we should apply? One is create a clock, set input delay and set output delay is for input to reg path and register to output paths. Then we should apply set max delay and set min delay for pure combinational paths, set false path for the false path, and set multi-cycle path for the multi-cycle paths. So all these constraints need to be applied. Right, after applying everything, how do we achieve the timing closure is the important question that we need to answer. If I have a setup violation, how are we going to solve that problem? And if you have a hold violation, then how are we going to solve this problem? That's what we need to understand. So that's what are the concepts of the timing closure. So first question is, how are we going to fix setup violations? I have a design and the design is not meeting timing because it has setup violations. So a setup violation occurs when the data arrives too late compared to the destination register's clock speed. How are you going to resolve the setup violation problem when you say? First thing is the filter to high order or confine logic to a smaller area. Because when we perform the optimization, when we do filter operation, then there are some optimization techniques that we can apply. We can tell the filter tool to do it. But what is required from our side when you say, we can rewrite the code to remove the logic stages. That is very important. That would give us a clear picture. Second thing, we can add pipeline. We all knew that pipelining means we need to reduce the data path. To reduce the data path delay, what we are going to do is, we are going to insert registers in the data path in order to ensure that the data path delay is reduced, but the throughput gets increased. Okay. And the last option you can see, that's what we did during the paper and pencil work. Slow down the clock, which is undisable. That is not the right method. And how are we going to fix hold violations? When you say, whenever your data is very fast, then you need to introduce buffers into the data path. So we can introduce delay into the data path by adding buffers or pair of inverters, but we don't want to do that because Quartus will automatically attempt and take that. So Quartus will attempt to fix automatically by adding delay in the data path. On some occasions, fixing hold breaks the setup. So it is very important that when we need to fix hold time, if you go on inserting buffers, there are chances that that will impact on the setup also. So fixing hold violations, there are chances that it can break the setup time also. All these things we should consider in our timing analysis. And then let us go to the summary page now. Don't take timing analysis for granted because it is very expensive if not dealt within the design stage. And we have to understand the scenarios and we should think about your constraints. And understand the digital electronics timing fundamentals so you can design reliable FPGAs and ASICs. That's the base idea. There are different timing analysis training which you can go through online that is available to you. I can just show one or two links now, and I request you to go through that. That will give you a good idea and getting hold on the timing analysis, and you will come to know how to apply effective timing constraints for the design. Right, so let me directly take you to a page. For example, so static timing analysis. Okay. Intel, you can say online training. Okay, so if you search, you can see that it takes you to the introduction to static timing analysis of digital circuits. So I will share this link with you in the chat. So I request you to go through that. So this will give you a good idea of how we can get into the logic. Okay, so I'll put that in the chat and I request you to go through that. So this particular training will provide you the idea of calculating the timing margin, and you can complete the paper and pencil exercise. After completing the paper and pencil exercise, you can gain experience in writing, analyzing, and correcting the timing constraints using the timing analysis tool. So you can get it. The idea is like you will be getting the concepts and arithmetic behind the digital logic, and you will also know how to calculate the maximum frequency, and you will also get hands-on practice in achieving the timing analysis. This is what I showed you. I request you to go through this because this is very critical and important for you to understand timing analysis and achieving the timing quotient. So with this, we are moving on to the hands-on session. I will share the labs in the Google Drive, and let us start the first lab. What would be your first lab? I will show you, and we can do the steps one by one. So what are the two important labs which we are going to do today? I will show that. The first one is using the timing analyzer PDF. This is our first lab. We'll share that with you using the timing analyzer. So this lab explains you to target it for some board. What I request is you can target any board. I request you to target it for D10 Lite or Cyclone 5. Okay, there is nothing to do with that. What is important is you have to constrain the clock, right? You have to apply clock constraints for this design. So the Verilog code is available in the lab manual itself. You don't need to search the Verilog code anywhere. Once I put that in the share, you can directly take this from the Google Drive and follow the steps. Apply the clock and you give some value and see why the design is not meeting timing. And you can explore and add some more values. That means you can search the clock and then provide and rerun the code with different values and see the output. So what is important is after analyzing the timing reports, you can see whether the design is meeting timing or not. See setup as well as the hold analysis, both. So clock period is 10 nanoseconds. You see whether it is meeting timing or not. Okay, so this is the first lab. And the second lab which you need to do, which I opened some time back, is the multi-cycle path lab. So design files, lab manual. If you open this lab manual, right, you can see the multi-cycle path example. Because the first lab is just only the project setup. right? And the second lab is based on the clock constraint. You need to apply the clock. So this one directly open because this has clocks. Because in the first example itself, since you are dealing with a single clock, you can directly go to lab 3 in the second lab, where you can take the multi-cycle path. Okay, and the lab files are available here. For performing multi-cycle path, you have to copy this into a C drive, and then you have to unarchive this file and follow the steps. This timing analyzer.qar you can do later also, no problem. To try to complete using the timing analyzer as well as this both. And you should also do the Verilog timing exception lab, which is the false path. I will put it into this. You try this example also. So there is a Verilog code where it has a false path, which I showed you now. You can try that example also. So there would be one example on applying timing constraints clock, another example on how to apply set multi-cycle path, the third one, how to ensure that the design is having a false path and how do we fix it. Okay, I will share all the details with you. I will be available online. So please complete the labs and then let me know if you have any doubts. We can get clarified. Okay, I will go ahead and put the lab manuals and you please start working on it. Are there any questions right now? So if there are no questions, let me immediately start. Put that in the Google Drive. You start working. I will let you know once it is done. Biplov, can you confirm whether all have received the materials? I have put that in the share. Can you please see that and then check whether all are able to see that?
Let me check, sir.
Yeah, in the day 2, I have put all the lab materials as well as the theory material.
Yes, sir. It has been shared in the Google Drive. All the participants can extract the data from the Google Drive already shared with them.
Sure, sure. Thanks, Biplov. Let them start. Yeah, thank you. Yeah.
Welcome, sir.
Hello everyone, just let me explain, okay, how we can apply all the timing constraints to the design, okay. So you open this using the timing analyzer lab. Okay, here we have applied only the basic clock, right? So let us copy this design. And we create a new project. A new project wizard you give and say, for example, C drive and say timing closure, something like that you take, or you say timing constraints. Okay, and what is the name of this project? Is add three numbers. So add underscore three underscore numbers. And say next, create this directory, add files, and then select the corresponding board like max 10. So 10M50 DAF 484 C7G. Select it, then next, finish. Okay, now what you should do is like file, new, click the Verilog HDL file and say paste it. You have the entire code right now. Okay, right now what we are supposed to do is first let us save this file. So file save as, we just check whether it is add three numbers, perform compilation. Now we will see one by one how to apply the timing constraints for this design. You can follow the steps if you want to do. Okay, I will apply the clock and then I will also tell you how to apply the set input delay and set output delay for this design. Okay, now let us start explaining the logic here. See, first we need to see the netlist viewer. Go to the technology map viewer. And here you can see that, okay, what are the different set of logic and how many paths it crosses, all these informations we can see here. Go to the tools, timing analyzer, and click create timing netlist. Okay, first apply the clock as mentioned in the lab note. Go to constraint, say create clock. What is the name of the clock? You say clock. And in the get ports, you list it and find out the clock, which is available in the matches. Select clock, bring that on the right hand side and say clock. Now, after providing the clock, you say two things. One is find first report clocks. That means we have to check whether the clock is reporting. Report clocks you do. And also, you have to check timing, report timing, setup analysis, say report. And you can see that it is from register to register path. There is no setup violation, means there is no problem. Also, we should check for hold. What you can also do report timing and select hold and say report. So setup also is positive, hold also is positive. But what we need to apply is input to register. Also from register to output path. Okay, is there any unconstrained paths when you say? You can see that. That you can try by checking here. Report unconstrained paths which will be available in the clock. See here, diagnostic, report unconstrained paths. Double click that. You can see that all the clock paths are constrained. Register to register paths are constrained. But input to reg path are not constrained and register to output paths are not constrained. Without constraining input to register paths and register to output paths, we cannot constrain the design. That's what we need to know the data sheet. That's what I showed you, a memory data sheet. Assuming that there is a device which transfers the data to FPGA and from the FPGA, another memory is getting the data. So then we need to provide set input delay and set output delay. Without providing the set input delay and set output delay commands, we cannot complete. How do we solve this problem? You need to go to constraints. Okay. Click here, set input to delay. Then you select the name of the clock. First, you give maximum. This is for the setup analysis. Give maximum and the delay value. For example, whichever you want to give. For example, I say delay value is, I say 8 nanoseconds. Let us assume. Or you take 10 nanoseconds. Or clock is 8, so you cannot give more than that. Okay, so you give 6 nanoseconds. Assume. So then you can see that all targets, right? You have to see here all underscore in. Right? Let us give a value. What happens? Let us see now when we give 6 nanoseconds. So this is for all the inputs. Okay. And this is for the maximum value. Similarly, we will give a set input delay for a minimum. So with respect to clock, give minimum and say a delay value of 3 nanoseconds and say all underscore in. Now this is for input edge path, and we also need to constrain register to output path. Go to set output delay, select the clock, give maximum, say 2 nanoseconds, and say target all underscore outputs, and say okay. So you say run. So now set output delay is given. Similarly, go to set output delay, clock, and say delay value 1, and again you say target all underscore outputs, and you say run. Now what we have given, see here, it is like all this add delay, right? So this has been taken. What is the problem is I have not given minimum. It's the problem. So again, you have to provide that minimum value better. So it is better to provide set output delay, clock, and you select minimum and say 1 nanosecond, say all underscore output. Take a minimum because otherwise it will take the same value for both maximum and that values can be replaced. Now you can take this path. Now you can see after applying all these things, you can take that all the paths are constrained. Now if you see report timing, you can see that input to reg path, right? Also the register to output path, all the paths are constrained. If you wanted to see more number of paths, click report timing. Instead of 10, you can ask for more. Do 30 and say, now you can see all the paths, register paths, you can see that. Okay. All the paths you can see. So it is very important and critical to constrain all the paths. Okay, so first complete the clock constraints. Then in the same design, you can extend for input to reg as well as for reg to output.